Welcome to the Fortify webinar, where we answer the question, can 3D printing solve your ESD manufacturing challenges? I'm Ben McDonald, Senior Applications Engineer at Fortify.
And I'm Randy Erb, Director of Materials. Electrostatic discharge is the release of static electricity when two objects at different potentials come into contact. Walking across the carpet in rubber-soled shoes can lead to an electrostatic discharge event. When you touch the door handle, you get a shock. This is a nuisance. This same level of electrostatic discharge onto a sensitive electronic device can evolve from a nuisance to a catastrophic failure and economic loss. In graver circumstances, electrostatic discharge can also ignite flammable materials. This is why electrically grounding yourselves at gas stations by touching the metal part of the gas pump is a recommended practice. In a lighter circumstance, buildup of electrostatic charge can attract dust or bioparticles that can range from an aesthetic nuisance to a health hazard. With the risks associated with electrostatic discharge, the need for ESD-safe materials has become a mainstay for many applications. Application spaces requiring ESD-safe materials include flammable material facilities like oil and gas, automotive paint, and even food processing. Electronic manufacturing facilities that assemble sensitive electronics. Hospital environments, food handling, and automotive interiors. One of the most effective ways to prevent the buildup of electrostatic charge is to allow the static charge to dissipate from the material component. This requires the material component to be somewhat conductive, but not so conductive that electrical shorting can occur. This chart shows the spectrum of electronic properties that range from conductive materials to insulative materials, as measured by the surface resistivity. The thresholds between the different categories may be slightly dependent on the application-specific definitions and requirements. For many of the ESD-safe applications discussed in this presentation, generally the target for material is to be on the more conductive side of the electrostatic dissipative range, or around 10 to the 6th ohm per square. Now Ben will walk us through some conventional and additive manufactured ESD-safe materials.
Thanks, Randy. So in the industry today, ESD components are manufactured in one of two traditional ways. So the first one being the injection molding space. A lot of your thermoplastics, elastomeric parts today are injection molded. And it's an all right solution. I mean, you're able to get high quantities for relative low cost per part, but you run into a lot of lead time issues. So you're looking at 6 to 8 weeks, if not more, to source a quantity of parts. Tooling costs are expensive. So really for your short run batches of parts, the bulk of your costs are going to be sunk into your tool itself. Once you get up into production scale quantities, it's much easier to swallow that pill, if you will. But for smaller quantities, that's a tough hurdle to overcome. And you're also looking at limited customization. I mean, you're building a mold tool, you're running parts, you're not changing up those parts at all. They're going to be the same part from shot 1 to shot 100,000. So it's really tough to customize those parts. On the other side of things, there's CNC machining for a lot of these materials. Now, CNC machining, it does enable a lot more customization because you're doing one part at a time. You're able to change up tool paths in between so that you're able to create some more unique parts. You're still looking at some of the same lead time challenges though, where it's going to take anywhere from 2 to 4 weeks plus to get your machine samples. It's also a very significant source of waste. So you typically start out with a sheet of whatever target material you're going after, and you're machining away a lot of that material. So there's a lot of waste generated during that process. Ultimately, it's not an ideal solution. And additive has jumped into the ESD market, and it helps overcome some of these hurdles. You're able to get parts in days, not weeks. So you're able to do quicker development cycles. avoid some of the delays caused by lead times for machine parts or molded parts. You're also able to avoid the expensive tooling from the injection molding space and a lot of the waste that you see in the CNC space. And on top of that, you're able to have some endless customization. One of the real drawbacks to the ESD and additive space right now is the performance. So you're able to get parts fast, a lot of customization for fairly cheap, but you run into issues where you have to choose between getting FDM parts or SLA DLP parts. For the FDM space, there are some pretty decent materials, but you're struggling with low resolution, poor surface roughness, and these parts are going to be anisotropic. So it really limits what you're able to do with these printed components. On the flip side, the SLA DLP space, that allows you to get parts that more closely represent a molded or a CNC machine part, but you have limits with the materials that you can actually process on these platforms. So one of the main things there is a lot of these ESD safe materials in the traditional manufacturing world, they're composites. So they take a base polymer and they add in fiber to help tune the properties of that material. You're just really not able to do that in the SLA world today. And that's where Fortify really steps in. So we're able to take additive manufacturing, take that process and pair that with the performance of polymer matrix composites. So those are those ESD safe materials, those highly filled materials that really enable true performance for valuable end use spaces. So the Fortify platform, it combines hardware, software, and materials in order to enable users to print these high value materials. So we start out with a robust printer platform, so our Flux series of printers. We pair that with the Compass software that enables us to do some really unique things with those parts that we want to print. And we pair that with our high value materials. So fiber filled materials, materials that have performance that enable really great applications. So we're going to dive into 3 different modules that really enable our Fortify Flux platform to get the most out of the materials that we're able to throw at it. We'll start out with a continuous kinetic mixing. So this module enables us to mix, heat, recirculate, and suspend fibers during the full printing process. So going from layer 1 to layer 1000, you're printing the same material with the same fiber concentration at the same viscosity. This is something that's integrated into all our Fortify printers, and it's really key for enabling us to print these highly filled materials. So this is a quick schematic of CKM, but essentially what you have is your reservoir, you have a mixer, and you pour resin into the mixer. That's where we heat, suspend, and meter into the reservoir out of our mixer. And in the reservoir itself, you have a continuous flow of fiber, call it fiber rich, but it's really homogeneously suspended fibers in that resin. The next up, we have our Flux print module. So all the Fortify resins, they're fiber-filled materials. What we're able to do with these fiber-filled materials is actually magnetically align particles in order to enhance material properties. One of the main things we look at is really just the strength of materials. So we're able to align fibers in the Z-axis, and that's what you're seeing in the video on the left-hand side here, is we're aligning fibers in the Z-axis. And what that enables is it allows us to have isotropic parts during that full print process. So rather than having our fibers be dictated by the layer lines themselves, we're able to orient those fibers in the Z-axis to overcome the traditionally weaker area of printed parts, being the Z-axis of parts. So this is really key for us to print these functional parts that we talk about. We'll take a little deeper dive into the flux print process here. So what we're doing is on a voxel by voxel basis, we're selectively aligning fibers and then curing. So you can see that we turn a magnetic field on to align in the Z-axis. We're only exposing the voxels that we want to cure with that select alignment pattern. And then we're able to either peel and print our next layer, or we're able to generate multiple fields within a given layer in order to really optimize the material properties of our parts themselves. With that, I'll turn it over to Randy to dive into our third module.
Thanks, Ben. An additional Fortify tool we'd like to highlight today has to do with the complexity of formulating filled photoresins within the DLP printing process. To highlight this complexity, let's quickly break down the anatomy of a layer during a Fortify print. First, on the left, we start with the plunge, where the build plate moves into a filled resin. We need to fully understand the rheology. Is it highly viscous, non-Newtonian, thixotropic? If the answer is yes to any of these, other DLP companies need to reformulate. Well, Fortify's hardware can handle this challenge. Second, if we apply magnetic fields during the print, we need to understand how magnetically responsive our filler is. Third, when we apply UV light to cure, we need to fully understand the photokinetics of these filled photoresins, understanding adsorption, depth of cure, and scattering effects. Fourth, as we peel, we need to understand the interplay between rheology of the uncured resin and green body mechanics of the cured part. Fifth, we need to understand sedimentation and flocculation rates so that we can continually homogenize the resin. Fortunately, all of this complexity is addressed in Fortify's Flux Developer platform. What is Flux Developer? Flux Developer is a software product that enables fast to market material formulation work to be completed in filled photoresins. By using Fortify's Flux Developer software product, you can take a materials formulation through a series of onboarding experiments in Fortify's FluxHost printing software to characterize photokinetics, build plate adhesion, sedimentation, rheology. With these details characterized, you can set up a material print configuration with the online Flux portal that will enable optimal DLP printing out of the gate. Monitoring printed part properties for key performance metrics, feedback to the materials formulation or material print configuration is straightforward and fast. Our customers and partners use Flux Developer to formulate filled photoresins and speed their formulations time to market. In addition, the material scientists here at Fortify also leverage Flux Developer to speed our own time to market for new formulations. By combining the Fortify tool set of Flux Developer, Flux Printer, and continuous kinetic mixing, we have realized two exciting and disparate formulations of ESD resin that are truly unique in the marketplace. On the left, we have Fortify's ESD HT resin that boasts an operating temperature up to 284 degrees Celsius. This material has been validated in challenging environments like solder reflow ovens. On the right, and at the opposite side of the spectrum, is Fortify's ESD elastomer. This material is the softest ESD material on the market and has a strain at break of 60%. Both of these materials lie within the static dissipative range and are ESD safe. Ben will walk us through the details of the ESD HT material first.
Thanks, Randy. So before we dive into some use cases for ESD HT, we'll take a look at the data sheet real quick. So ESD HT, it's a fiber reinforced material. Like Randy said, it's able to operate in temperatures up to 284 C. So it's a really ideal candidate for high temperature applications like your solder reflow oven, things of that nature. On top of that, it's boasting a 10 to the 6 ohms per square surface resistivity. So it's really ideal for dissipative applications. And it has a best-in-class resolution and surface finish. So you're able to pair the functionality of traditional materials with 3D printing resolution and surface finish. And we'll take a quick look at a comparison of our ESD HT material compared to some of the other materials on the market. So if you take a look here, on the left-hand axis for this graph, the vertical axis, we have our HET, and on the horizontal axis, we have our Young's modulus. And you can see that Fortify is really in a space of its own when it comes to stiffness and heat deflection temperature, where everyone else in the market to date is operating below 150 C and below 4.5 GPA for their youngest modulus. So they're really not great candidates for some of the high temperature applications, really the high value applications in the ESD space. So first up, we'll start off with a solder reflow tray. So a solder reflow tray, it's used to fix your PCBs while they go through a thermal bake process in order to essentially melt and cure solder. Some of the needs for something like this are able to withstand temperatures up to 250 C, which our ESD HT is more than capable of doing. You also need to be able to hold a tight tolerance in order to properly fixture these PCBs. If you're not able to hold that tolerance, then you'll run into issues, either fit issues where PCBs don't fit into position, or these PCBs will be loose and could potentially get dislodged, messing up your components and ruining that whole reflow process. And finally, this board needs to be dissipative because you do not want an ESD vent damaging a component on your board and ruining the full production process here. So for the solder reflow trays, Fortify's ESD HT material is really uniquely suited to handle the demands of that reflow oven. Next up, we have SMT nozzles. So SMT nozzles are there for surface mounting of PCB components on a solder reflow board. What's unique about these nozzles is that they have some very small or complex geometry. We're really looking at the through holes in the center of these components. Those through holes, those are for actually pulling a vacuum force on the components and placing them on your PCB board. These through holes are very tough to manufacture traditionally and with a lot of additive technologies, but with our Fortify platform, we're able to resolve some of these through holes that get down to below a millimeter in diameter. We're able to resolve those due to the DLP nature of Fortify printer. And this is really where stiffness comes into play. These components, they're undergoing vacuum, they're being pressed down on top of PCB components. They need to be stiff in order to properly position components where they need to go and to withstand the repetitiveness of that process. So for the surface mount nozzles, Fortify's ESD HT is also, again, uniquely suited for this process. So what we have here is a PCB carrier. This is really, it's great for just general PCB handling. When you're going throughout your lab space, your office space, what this is going to enable is it's going to allow users to pick up this tray rather than picking up individual components. You're going to prevent any sort of static discharge from jumping to the boards while you're transferring these trays. It's great for storage and really just handling PCBs in a safe manner so that you're not adding any unnecessary risks to this process. And with that, I'd like to call out Fortify's ESD HT pilot program. So we're currently running a pilot program for our ESD HT material, looking to get customer feedback and get this material in your hands. So what we're doing is for a couple different geometries, including tensile bars, surface resistivity coupons, and a fine feature test, we're sending out these samples free of charge so that customers or end users can validate this material to see that it really works and can learn about how to get more parts out of this material. And with that, I'll turn it over to Randy for our ESD elastomer material.
Thanks, Ben. In addition to our ESD HT material, Fortify has recently unveiled an ESD elastomer product. This is the first ESD elastomer for DLP on the market, which opens the door for high resolution, high production capacity, and fast customization for this class of material. ESD safe components printed from Fortify's ESD elastomer are very soft, have a very high tear strength, and are static dissipated with a surface resistivity of 10 to the 6th ohm per square. These compliant ESD safe components can be used in applications including boots or caps and enclosures. For example, for companies working with changing printed circuit board designs, bespoke ESD safe boots can be designed and printed within a day using Fortify's ESD elastomer. These components can then be press fit onto a printed circuit board to protect sensitive electronics during the manufacturing process. In addition to being static dissipative, with a Shore A hardness of 70, Fortify's ESD elastomer is the softest ESD elastomer on the market available. This is softer than current options, even outside of the additive space. This compliance allows for snug press fit connections with high precision. Fortify's ESD elastomer has a tear strength of 24 kilonewtons per meter and an elongation at the break of 60%. One of the challenges of working with very soft materials is the possibility for strain-dependent properties. Compressing dissipative materials can drive electric percolation at the microscale, increasing the material's conductivity into the EMI shielding or even the conductive range. Fortify's ESD elastomer has been formulated to accommodate large strains of up to 25% while remaining safely in the dissipative range. Here at Fortify, we are excited to bring the ESD elastomer to market. The highest resolution, market-leading softness and static dissipative properties enable Fortify's ESD elastomer to address broad application spaces, from compliant fixtures and electronic handling trays to soft robotic grippers to boot caps for PCB manufacturing. We are engaging with customers today to explore opportunities for our ESD elastomer product. The intent of the webinar was to highlight the space of ESD safety and showcase the growing suite of Fortify ESD safe materials. If you are interested in Fortify's ESD-HT for high temperature applications, reach out with questions or to be part of our ESD-HT pilot program. If you are interested in Fortify's ESD elastomer, contact Ben, me, or our sales team. That concludes Fortify's webinar on 3D printing ESD safe materials. We thank you for your attention and look forward to hearing from you.
Awesome. That was really good.